Hello again. This is video lecture 24.4, and we're going to study section 7 in chapter 24, where we're going to talk about the electrical potential energy of a system of charged particles. Okay? Electric potential energy of a system of charged particles. Energy. Not electric potential energy. It's so easy to get those ideas confused. Okay, so here's the upshot, the big picture. If you have some configuration of particles with charge sitting somewhere in space, there is some stored electrical energy just in them being there. And the way to think about that is that we, as agents, external agents, are going to have to do work to configure the charges the way they are. Somebody's going to have to take them and drag them and put them where you want them. And when you do that, they're going to be pushing on each other. So you're going to have to, you're going to have to push. And so the point is you're going to do work. And just like you do work when you compress a spring, and that results in stored energy, when you do work on charged particles, that results in stored energy, U electric. And we want to be able to calculate that. Because if we store it, then we can get it back later. Just like if we compress a spring, we can get that energy out by letting it relax and letting it make something move. Okay. So it takes work from an applied force, that's us, to assemble a system of point charges. So such a system has electric potential energy, U elect. We want to calculate that. That's the whole purpose of this video. And so the first question is, how do you calculate U elect for a system of point charges? Well, we actually use ideas we've already talked about, but I'm going to go through them. Here's one idea. I'll write it over here to the side. Change in electric potential energy of a system is the negative of the work done by the electric force on that system, okay, when charges move around. But now here's what we're going to imagine. This is the thought experiment, and this is how we've decided. It's kind of like choosing a reference point. We're going to start with all the charges involved way out at infinity, infinitely far away. We have kind of a blank slate, and there's no charges at all, and so there's no stored energy. Start out with nothing. And you bring the charges in from infinity one at a time, and put each one where you want it, one by one, starting from infinity, where the stored energy is zero. Okay? That's part of the big idea here. And if we're going to assume that each particle starts at rest out at infinity and ends up at rest where we want it. So there's no change in its kinetic energy. K final minus K initial is zero. And the work kinetic energy theorem tells me, in such a case, the work that I do, the applied work, is just the negative of the work the electric force does. Okay, so the work I do is going to end up equaling however much the electric potential energy changed. Okay? Now remember, all the charges start out at infinity where the potential energy is zero. So in this delta U electric initial is zero. So the delta U electric really just boils down to U elect final is equal to how much work I had to do to bring the charge in from infinity. Now I combined that expression with one other idea from this chapter, right there. If I've got moving charges, then the change in the electric potential, delta V, is equal to the change in the electric potential energy, delta U elect, over the charge that was moved. Delta V equals delta U elect over Q. Let's just rearrange that. Delta U elect equals Q times delta V. But the initial values of the U elect and the V are zero, so that's really just U elect final is Q times V final. And I actually have that equation written here in big font. big type, okay? And so what I have then is the formula I need. That's it right there. It's also here. The final electrical potential energy that will result when I take a charge Q that was sitting out in infinity at rest and bring it, pull it, and put it where I want and leave it there, okay? The electric potential energy then is the charge that I moved, Q, times the electric potential in volts, V, at the final location where I put the charge, Q. That's all we have to do. We've got to find the electric potential at the final location where we put that charge Q and multiply that by Q. So let me show you how this plays out. We can use this idea for any system of point charges, any system, no matter how complex. Let's apply it to the system you see here under number 2. Okay? Let's just imagine that this is the system of charges that we have. This is the configuration of the charges in their final form. Charge number 1 has charge Q1 and has been put right there. And it's positive charge. Charge number 2 is positive, charge Q2, and it was put directly, if you like, above charge 1 and at a distance little d from it. And then charge number 3, which is also positively charged, Q3, is put right there, due to the right of charge number 1, and a distance d from charge number 1. So what we've kind of got here are 3 corners of a square with a charged particle at each of those corners. And I want to know how to calculate the total electrical potential energy of that configuration. Because I, as an agent, am going to have to do applied work to get those charges there. And that's why there's energy stored. So we do this as kind of like thought experiments. We do it in a sequence of steps. You start with all 3 charges out at infinity, just waiting. And my region here is blank, empty. No potential energy, if anything. Step number 1 then is no charges present, nothing. Blank slate, tabula rasa. Step number 2, bring in one of the charges. It doesn't matter which. I'm going to decide to pick Q1 from infinity, starting at rest and ending at rest, and put it where I want it. Now remember, particle 1 is put here, so that's where I put it, okay? Now, remember, there are no other charges there, yes? So actually, I don't have to push it to get it there, okay? Yes, I have to speed it up from rest and slow it down to stop it, but there's nothing continually tugging on it that I have to overcome. So I don't have to do any network to get this first charge in, right? Since no other charges are yet present to be tugging on particle 1, I don't need any net work to do it. W applied is 0. So, no stored energy. If you didn't do any work, if you didn't put anything in, you don't have anything stored. Just like in your bank account. If you don't put anything into your savings, its balance is 0. Say it another way, in a charge configuration, whichever charge you bring in first and put at its location, you get that one for free. All right, next step, step 3. Now, we're going to have to nail down charge number 1 because we're not going to allow it to move. So once you get charge 1 where you want it, nail it down so it won't move. And that force from whatever is holding it down won't do any work because charge 1 isn't going to move. All right, so with charge 1 nailed down, step 3. Let's bring in a second charge. It doesn't matter which. Let's say Q2. From infinity, with Q1 fixed in its place. And put charge 2 at its specified final location, which is up here. Distance d from Q1. When this process is done, the electric potential energy of Q1 and Q2 together is ULEC. All right, I'll write it over here to the side. I take the charge that I moved, Q2 times the net electric potential at the location where Q2 is put. Okay? All right, so Q2 was the charge that was moved. And then V net here is the net electric potential at the final position of Q2. And that potential is due to the charge that is already there, Q1. But that Q1 is just a point particle. And we know how to find the electric potential of any point particle, in this case Q1. You take the charge of the particle in question, Q1, over 4 pi epsilon 0, and we keep saying r here, right? But you have to understand, r means the distance from where you are to the particle. So in this case, the r is the distance from where we are, that's where Q2 is, to where the particle is. Well, that's Q1. Well, that distance is d, and that's the symbol then you need to use there. So at the end of this stage, here's how much electrical potential energy there is. U elec. Now it's just for bringing in Q2. It's Q2 times V net, and V net is Q1 over 4 pi epsilon 0. So altogether, you've got Q1 times Q2 over 4 pi epsilon 0 d. And that is how much energy you need for step 3. Now, in this case, there's one more step, because we have to nail down charge 2, can't let it move. Now we go out to infinity and we snatch charge 3, grab it, and bring it and put it at its specified final location, which for particle 3 is there. Also a distance little d from particle 1. And we'll have to do work to get particle 3 to do this, because they're all positive charges, and so it's not going to want to do it, and we're going to have to drag particle 3 in. And that's going to add more energy. Okay? All right, so step 4 then. We're bringing in the third charge, Q3, from infinity, with Q1 and Q2 fixed in place. The work required to perform this is U elec equals the charge you had to bring in, Q3, times the net electric potential at the final location of Q3 due to the charges that were already there. Okay, so that's what the V net here means. And I've also got it written over here. The net electric potential at the final position of Q3 due to Q1 and Q2. Well, here's Q3. So what's the V net? The net electric potential here due to Q1 and Q2. 2 charges there, right? All right. Well, from the Q1, you have this term. Q1 over 4 pi epsilon 0 d. You see that? Because particle 3 is a distance d from particle 1. Now, what's the contribution to the potential at particle 3's location from particle 2? That will be Q2 over 4 pi epsilon 0 r, where that's the r, right? For Q2, that's the distance from Q2 to where particle 3 is. Note from just geometry that r is the square root of 2 times d, Pythagorean theorem. So that contribution then is Q2 over 4 pi epsilon 0 square root of 2 times d, and those two expressions get added together. So Q3 times that V net is the electric potential energy that we then have resulting from bringing in Q3. We're not quite done. There's still one more important step. We've got to find the total electrical potential energy of the entire system. That's the total work we had to do to assemble the system. So that's this line right here. That's the electric potential energy involved in bringing in Q1 first, from infinity, plus the electric potential energy involved with bringing in Q2 after Q1, plus the electric potential energy involved in bringing in Q3 after Q1 and Q2. Okay? All right. Now, we have an expression for each one of those. The electric potential energy involved in bringing in Q1, nothing. That was the first one. That was a blank slate. I got that one for free. Next, the electric potential energy for bringing in Q2 after Q1 was just that. Q1, Q2 over 4 pi epsilon 0 d. Then the most complicated piece is the electrical potential energy involved with bringing in Q3 after Q1 and Q2. And that has two pieces to it, and it's all right here. Q1 times Q3 over 4 pi epsilon 0 d plus Q2 times Q3 over 4 pi epsilon 0 square root of 2 times d. And that's the final answer for the stored electrical energy in the system of 3 charges in this configuration up here. Okay? Now, every configuration, you can have all kinds of configurations with all kinds of charges. So you have to understand the process. You just use this process to get the total stored energy. Now, I do have some comments that might make it a little bit easier to appreciate this result. First comment. Let me make sure it's a little bit lower so some of that's visible. First comment. Suppose my system consists of only 2 particles. Charge 1, Q1, charge 2, Q2, separated by a distance r. What's the electrostatic potential energy in that case? Well, all you really got to do is go up to my answer up above and throw out all that stuff that had to do with particle 3, because there isn't any particle 3. And you see that all you've got then is a very simple result. If it's a 2-particle system, the stored energy, U elect, is Q1 times Q2 over 4 pi epsilon 0 r. So I'm talking about a situation like that. 2 particles, Q1, Q2, distance between them, r. That's the formula for the stored energy, okay? Now notice something important. The value of the U elect in this 2-particle case, the sign of it, I should say, depends upon the sign of the product, Q1 times Q2. See the product there in the numerator? That product could be a positive number, or it could be a negative number. If it's a positive number, then the stored energy is positive. The potential energy is positive. That's because I have to do, it turns out, overall positive work to make the whole thing, put the whole thing together. That would happen if the 2 charges have the same sign, either both positive or both negative. Because in either case, I'm going to have to push that second one in. It's not going to want to go. That results in positive stored energy. Now, the second situation is something you might not be quite so comfortable with. Negative stored energy. Negative U elect. And that would happen if the Q1 times Q2 value was a negative number. And clearly that would happen if one of the charges was a positive charge and the other charge was a negative charge, because then the product is negative. That means I have to do negative work to assemble this. That means I have to kind of hold the second particle back as it goes in so that it doesn't speed up on me. And that's because if they have opposite signs of charge, they're attracted. So you can have negative stored energy. And it means you had to do negative work to configure the charges. And that means they want to come together. Versus if it's positive stored energy and you did positive work, they didn't want to come together. Now that's if you have 2 particles. If you have a system with any number of point charges, like n of them, the most straightforward way, I think, to think about calculating the total stored electrical energy, U elect. I've written it out here mathematically. It looks more complicated than it really is. Here's what it says to do. Sum over all possible pairings of charge and don't double count them. So let's just take a three-particle system. Well, let's do a simple, different geometry. How about that? Q1, Q2, Q3. Take all possible pairings, like 1 with 2. You got to know the distance between them. I'll call that R12. You'll have a contribution to U elec from just those two. That would be that. Q1, Q2 over 4 pi epsilon 0 R12. Then another pairing is Q1 and Q3 with some distance R13. And the contribution to U elec from that pair is Q1, Q3 over 4 pi epsilon 0 R13. Then there's one other distinct pair in this case. Right. 2 and 3 with some distance R23. And the contribution to the potential energy there is Q2, Q3 over 4 pi epsilon 0 R23. And then just add those up. That's what this formula says to do. Don't count a pair twice. Don't do 1 and 2 and then 2 and 1. Each distinct pairing of 2, right? Pairing 2. Take the q's to multiply them over 4 pi epsilon 0 times the distance between them. And then add those terms up. So you would add that plus that plus that in that example, like that little picture I just drew. And that's how you do it. Now, there's more things to know, and I just said this. If the U electric overall is a positive number when you're done, then our applied force did positive work to assemble the charges. They had to be pushed into the given configuration. If U electric is negative when we're all done, then our applied force had to do negative work to assemble the charges. They had to be held back as they came in. And the final answer that you get for U electric does not depend on the order in which the charges are assembled. Doesn't matter which order you bring them in from infinity. Okay? All right, so let's just close the video with a little class engagement situation for Blackboard. And it goes like this. We got a figure, you can see it here. It shows two charged particles that are fixed in place. Q1 is positively charged with a charge plus little e. Q2, which is clearly at the origin of an xy coordinate system, also has positive charge plus 2 little e. We are going to take a third particle of charge Q3, that should say Q3 equals plus little e, and we're going to move it along a circular arc around the origin, starting at point A, going around the circular arc to point B, there on the y-axis, and then on around until I get a half circle at point C, there. Okay, centered there at the origin. Here's our task. Rank these 3 points, A, B, and C, according to the total electrical potential energy of the 3-particle system, the U elect total for the 3-particle system, right? There's Q1, Q2, fixed where you see them, and then Q3 that you're going to move along that circular arc. Rank the U electrics values for the 3 points, A, B, and C, greatest to smallest. Okay, now we'll have a class video to go with this in which we'll do a Wiley Plus problem. Okay, and that's all then for this video.